Hello again. Let's continue chapter 8 and talk about the limbic system. Limbic system is your emotional system of the brain. It's not one part of the brain, it's a collection of different segments of the brain, and altogether it's called limbic system. In the past, the limbic system was called rhinencephalon or smell brain because, as you will see in a few minutes, a part of this limbic system that deals with emotion is attached to your olfactory sense or sense of smell. The area of the brain that's involved with limbic system are a gyrus in the brain is called cingulate gyrus, amygdala, hippocampus, septal nuclei, anterior insula, hypothalamus, and finally thalamus. Let's take a look. In this picture, you can see some areas that deals with emotion. Let's start from here. You can see this is the olfactory bulb, is the one that brings the sense of smell in. This is part of your limbic system. It's called olfactory bulb. And then, as you can see, olfactory bulb is going to attach to a nucleus. It's called septal nuclei. Septal nuclei also is part of your limbic system. This is a corpus callosum, is the one that we talked before that attach right and left hemisphere to each other. Right above corpus callosum, there's a part of the brain that's called cingulate gyrus. A gyrus simply means a small bulginess of the brain. This is also part of your limbic system. Another part of the brain is called hippocampus. We already talked about hippocampus briefly. We said hippocampus deals with memory. Hippocampus also is going to relate to your limbic system or emotional center of the brain. If you follow this picture, you can see this part of your temporal lobe has a deep nucleus inside. It's called amygdala or amygdaloid complex. This is also is part of your limbic system. This area of the brain that is called hypothalamus has a nucleus that this nucleus is called mammillary body. Mammillary body is part of hypothalamus. And this mammillary body attaches to part of the thalamus. This area is the thalamus. And this part of the thalamus is called anterior nucleus of thalamus. Both of them, the thalamus and hypothalamus, specifically mammillary body and anterior nucleus, are part of limbic system. As you can see, mammillary body is going to use fornix, this structure, and attaches to the hippocampus. All the structure I mentioned, they belong to the limbic system. Let's review one more time. Olfactory bulb, your septal nuclei, cingulate gyrus, hippocampus, amygdaloid complex, mammillary body, anterior nucleus, fornix, and finally, insula that is not shown in this picture. So let me show you the insula. This is a lateral view of the brain. This is the front of the brain, this is the back of the brain. You're looking to the brain from the side. That means from this direction. As you can see, there is a line here that's called lateral sulcus, this one, this line. If you put a retractor here and pull this part up and pull this part down, you're going to see something like this. So here I pull this one up, I pull this one down, and see under that, there's part of the brain is called insula. Insula also is part of your limbic system. If I show you another picture, you can see everything here very nicely. That blue one is going to be a cingulate gyrus. This is your hippocampus. As you can see, hippocampus is going to attach to mammillary body by the fornix, and also realize amygdala is part of this structure, as is thalamus. If you look at this picture, you can see this is my corpus callosum. Above this one is not shown, but it must be cingulate gyrus. This is my hippocampus, and this structure that you see here that is going to continue toward back is called fornix. If I want to increase the magnification, you can see this is your fornix. This one is fornix. This is your hippocampus. This part is your thalamus. Septal nuclei, as you can see, is connected to the olfactory bulb, but has nothing to do with the sense of smell. Septal nuclei deals with reward and reinforcement. If you destroy septal nuclei, it's going to create an aggressive behavior. Since we learned the structure of the limbic system, let's talk about the function of the limbic system. We said limbic system is going to deal with emotion. And remember, your emotion can change your behavior. So in a sense, we can say limbic system not only establish your emotional state, but also is going to relate to your behavior. For instance, your aggression or fear is a result of the function of limbic system. Also, we can link this emotion to the conscious or intellectual function. We all know that when your emotion is down and you're feeling depressed, your intellectual function is going to get affected by that. We also know that limbic system is going to link this intellectual function and conscious into unconscious and autonomic function. For instance, some people, when they hear a news which is going to affect their emotions so strongly, they may have some autonomic response. In other words, they may throw up. They say that they have pain in their stomach. So my point is, the limbic system is not only about your emotion, but has many other links to different parts of the brain, including your behavior, including your intellectual function, including your unconscious mind or autonomic functions. When your emotion is up or down, your memory also is going to get affected. When you are depressed and you're sad, probably you cannot remember things. When you are feeling good about yourself, probably you're going to remember things much better and your attention will be much stronger. Here I list some of those emotions and see which part of the limbic system is going to deal with. For instance, fear is more related to amygdala and hypothalamus. Hunger and satiety, your feeding behavior more is related to the hypothalamus. The limbic system is going to deal with mating. It seems like all part of limbic system is involved during the mating behavior. Hypothalamus and other region of limbic system also is going to control your goal-directed behavior. As I said, when your emotion is up, when you feel good about yourself, probably you're going to achieve more. Aggression is going to deal with amygdala and hypothalamus. There is a circuit in the limbic system, we call it Papez circuit. Remember a few minutes ago we talked about how we're going to connect hippocampus to mammillary body and then later to the thalamus. That circuit is called Papez circuit. Papez circuit attach hippocampus to mammillary body and then it's going to send this neuron to thalamus. Later, thalamus is going to send this neuron to cingulate gyrus, which send the information back to the hippocampus. So as a result, as you can see, all these areas are attached to each other by a circuit we call it Papez circuit. When someone cannot remember things or lose the memory, we call it amnesia. Besides the area that we mentioned a few minutes ago, there are other parts of the brain that deals with memory. For instance, we know caudate nucleus is part of the memory. If you don't know where caudate nucleus is, I'm going to show you in a few minutes. Also, another part of the thalamus is called dorsomedial nucleus, deals with memory. We mentioned a few minutes ago that amygdala is important in learning fear responses. Amygdala is going to deal with fear memory. Prefrontal cortex, which its main function is about solving complex issues, deals with working memory or short-term memory. Also, hippocampus, as we mentioned many times, deals with acquiring new information. Hippocampus also is going to consolidate short-term memory and turn it into long-term memory. Inferior temporal lobe is an area that stores long-term visual memory. And finally, people with the mammillary damage, they usually show confabulation. In other words, when you ask them about some events in the past, because they cannot remember, they're going to make up a story. Not intentionally, but the brain is going to fill the gap. These people, they show retrograde amnesia. That means they cannot remember old information. This picture shows all this structure together in a very nice view. This is your cingulate gyrus, this is your hippocampus, amygdala, and you can see this is your olfactory bulb, and this is your thalamus. This part would be your fornix. Let's see how short-term memory or long-term memory works. In the case of short-term memory, when you're trying to learn something, let's say you're listening to this lecture, there is going to be some synaptic changes. You're going to release some neurotransmitter, most importantly, glutamic acid, which are not going to last long. If you repeat this information over and over and use that circuit over time, then you're going to create long-term memory. In the case of long-term memory, you're going to create some structural changes. You're going to create more synapses among neurons. To store this long-term memory, you have to consolidate the information. Consolidation of the information happens in the temporal lobe, in the hippocampus and amygdala. Let's take a look at these synapses. This type of synapses, that input is going to come and then is going to go back and make a circle, is called reverberating circuit. When you're learning information as you're learning right now, you're going to create this type of circuit in your brain. This is going to create a short-term memory. If you don't continue and you don't practice this information, this type of circuit is going to be gone. Just like when you type something on your computer and you don't save it, the information will be gone. Realize that a short-term memory involves a recurrent circuit we call it reverberating circuit. This is very temporary. If you interrupt this circuit, then your memory is gone. However, in a long-term memory, you create a permanent change in the neuron and create permanent synapses, and as a result, you can remember this information for days or months or even years. We have different type of long-term memory. One is called implicit memory, one is called explicit memory. Non-declarative versus declarative. Implicit memory is learned unconsciously. For instance, you know that touching fire is going to burn you. This type of memory is learned unconsciously. Declarative or explicit memory is a memory that you learn consciously with practice. There are different forms of explicit memory. One is called semantic memory, or the other one is called episodic memory. In the semantic memory, you're learning the facts. You have some knowledge that you can use in your regular life. However, episodic memory is a memory of time, places, events. There's a table in your book that explains different type of memory. Episodic memory versus semantic memory. There's another type of memory, it's called procedural memory, can be explicit or implicit, and that is learning how a thing works. For instance, driving or tying your shoes. These are procedural memories, can be explicit or can be implicit. Another type of memory that we mentioned a few minutes ago is called working memory. Working memory is a very short type of memory. For instance, if I ask you to memorize a phone number, you may repeat it a few times, but it's going to last only for a few seconds, usually 30 seconds, and after that it's going to be gone. That's why it's called working memory. People who abuse alcohol, they damage their mammillary body and mediodorsal nucleus of thalamus. Why is that? Because usually these people, they don't eat anything. Their only diet is alcohol, basically. As a result, after a while, they're going to have thiamine deficiency. Thiamine or B1 is a vitamin. Lack of B1 is going to damage your mammillary body or mediodorsal nucleus. Thiamine deficiency is going to create a syndrome. It's called Wernicke-Korsakoff syndrome. And in this syndrome, you will see your mammillary body and thalamus will be damaged. We mentioned long-term potentiation during our discussion in the previous section. We said in long-term potentiation, you create a sustained changes in the quality and quantity of connection. We mentioned that long-term potentiation is going to increase excitability of a synapse after high-frequency stimulation. And we said that glutamate would be important neurotransmitter for this one. So let's take a look at the function of the glutamate to create long-term potentiation, to create memory. Let's see how this one works. This area would be your hippocampus. Let's say one neuron is going to bring the information, and at the end of this neuron, we're going to release glutamate. Glutamate is going to sit on the second neuron on the receptors that we have on the postsynaptic neuron. Glutamate, as you remember, has two receptors, AMPA and NMDA. Glutamate is going to sit on the AMPA, and AMPA, being a direct channel, is going to open up and sodium is going to come inside the cell. So the reason you open this channel is because of glutamic acid. When sodium comes inside the cell become partially positive. Remember, glutamic acid also is going to sit on the NMDA receptor. When glutamic acid sits on the NMDA receptor, this channel is not going to open. Why? Because inside this channel is being plugged by magnesium. So glutamate is going to sit on AMPA and opens it and brings the sodium in. Also is going to sit on NMDA, but is not going to open this channel because this channel is being plugged by magnesium. To remove magnesium, we have to partially depolarize the cell. So entrance of sodium from AMPA would be essential for this channel to open. When the cell becomes depolarized, that is going to kick this magnesium out. This depolarization that kicks the magnesium out is called electrostatic repulsion. We call NMDA as a coincidence detector because it requires presynaptic and postsynaptic events. Presynaptic when the glutamic acid sits, postsynaptic when you depolarize the cell. After magnesium is out, these channels open and sodium and calcium together is going to enter the cell. That is going to create a very significant effect. When the calcium comes inside the cell, calcium is going to attach to a protein called calmodulin, and calcium calmodulin together, they can activate an enzyme called CAMK2, calcium calmodulin protein kinase 2. When the calcium calmodulin activates CAMK2, CAMK2 can push those AMPA receptor that is inside the cell to the surface and increase the number of the AMPA receptor. As a result, when glutamate is released, it's going to bring more sodium inside. Also, when the calcium comes inside the cell, there's going to be a longer term effect, and that is calcium is going to get inside the nucleus and binds to the calmodulin inside the nucleus. And when the calcium attached to calmodulin inside the nucleus is going to activate another protein kinase, it's called CREB, or it's called cyclic AMP response element binding protein. We're going to talk about CREB or CAMK2 in detail later. I don't want these names to scare you, but it's just a protein. It's just a protein kinase. So calcium is going to enter the nucleus, attaches to calmodulin. Calcium calmodulin together is going to activate another protein kinase called CREB, or cyclic AMP response element binding protein. This CREB now is activated and act like a transcription factor. And transcription factor, as you know, is going to change the gene expression. In this case, the CREB is going to activate a piece of gene and produce more mRNA and protein, and that protein is going to create new dendritic spines that has AMPA receptor. In other words, you're going to create new attachment between your neurons. Let's take a look at this picture. All of these spines you can see is going to come out of the dendrites. This number of the connections is a structural change that happens after you practice something and you learn it more and more. So again, when you're learning something, at the beginning would be only changes in the neurotransmitter release. But when you practice something over and over, then it's going to create some structural changes, and that is because of activation of the CREB inside the nucleus that produce new protein, and that protein is going to create a bunch of permanent connections between your neurons. Now, remember we talked about long-term depression. Let's explore this one here also and make sure we understand. Let's first learn about the definition of learning. Learning can be either non-associative or associative. In non-associative learning, which is exemplified by habituation, a repeated stimulus causes a response. For instance, when you move to an area that is next to BART or train, every time the BART or train is going to pass, you're going to wake up. However, after a while, you learn that the stimulus, which is here the noise of the train or BART, is not very important. So as a result, after a while, the response, which simply is waking up, gradually diminishes because, again, you learn that the stimulus is not important. This is called habituation. Now, since you understood this one, let's go to synaptic plasticity. Synaptic plasticity is the fundamental mechanism that underlines learning. So we need to know synaptic plasticity because it's going to explain how learning process take place. You need to realize that synaptic function is variable and depends on their level of activity or traffic through the synapse. So when two neurons attach to each other, the function of this synapse can be variable based on how much this synapse is active. The responsive of the postsynaptic neuron, which we call it as synaptic strength, is not fixed. How much the postsynaptic neuron is going to respond is variable, and it depends on previous level of synaptic traffic. If you had higher synaptic traffic before, your synaptic strength or your postsynaptic neuron response can be varied. Let me give you an example. In the phenomenon which we call potentiation, repeated activation of a neuronal pathway leads to increased responsiveness of the postsynaptic neuron. In other words, if you send impulse back to back in one pathway, that is going to increase synaptic strength, is going to increase the response of the postsynaptic neuron. The period that this postsynaptic neuron enhance its response may be varied, may be very brief for only milliseconds, or may last for days or weeks. If it lasts longer, if it lasts for days or weeks, we call it long-term potentiation. However, in habituation, increased synaptic activity causes decrease in responsiveness. In other words, the more you hear the noise of the train or BART, the less your postsynaptic neuron will respond. So do you see that the synaptic strength not always increases after multiple stimulation? Sometimes multiple stimulation decreases postsynaptic neuron response, and the best example for that one would be habituation, or we call it long-term depression. Why that happens? Well, simply put, the answer is sometimes multiple stimulation or multiple impulse, yes, is going to bring calcium inside the cell, but instead calcium is going to activate an enzyme which is a phosphatase. Activation of phosphatase, as you remember, phosphate is going to remove phosphate. Activation of phosphatase is going to go to AMPA receptor and remove the phosphate attached to AMPA receptor. As a result, is going to internalize AMPA receptor from the surface area of the cell. As a result, you're going to have less AMPA receptor here. So remember, if you stimulate a neuron in the long term, you may depress the synapse. How? Calcium is going to activate phosphatase, and as a result, phosphate is going to come and remove phosphate attached to AMPA. By removing phosphate attached to AMPA, the AMPA receptors is going to become internalized, is going to get back inside the cell. As a result, you have less AMPA receptor on the cell membrane. One of the important enzymes that probably you need to know that removes this phosphate is a phosphatase and is known inside the hippocampus. It's called calcineurin, and calcineurin, as you can see in this picture, is going to come and remove the phosphate. As a result, the AMPA receptor will be internalized.